you can proceed. Many
Okay,
thanks.
thank you. So this is the outline. I will talk a little bit about task-based programming and our OmpSs programming model, and then concentrate on OmpSs at FPGA. Mercurium is the compiler, and AIT is the automatic integration tool that we use to drive the vendor tools. Then some examples and evaluation. And I have also added a section on how to exploit OpenCL kernels, also using OmpSs. And then I will conclude. By the way, there is a demo also. Here at BSc, we are promoting for heterogeneous systems and big systems the task-based programming, which consists on getting the application, breaking it into small or not so small pieces, depending on the granularity you want and the overhead that the runtime system supports. And this is actually the graph that we get from, it's a typical graph from OmpSs that resembles the execution of Cholesky, okay, which is based on 4 different kernels that you see here in 4 different colors. One of them, I would say the blue one, is matrix multiplication. And the others are different versions of linear algebra algorithms. So here the goal is to execute as efficiently as possible these tasks and potentially allow them to target GPUs and FPGAs. So here I'm going to concentrate on targeting FPGAs, how we do that. Overall, at BSc, we call the global programming model, this is like everything is superscalar, no? It's star SS, star in the sense of asterisk, okay? And we have 2 main implementations. The OmpSs implementation targeting SMP, GPU, FPGA, small clusters, and we also have OmpSs targeting cloud of FPGAs that we have tried with IBM in Zurich. And we have a second implementation, which is actually developed by another group at BSc. The group is led by Rosa Badia. And the goal is more for cloud applications. So this is COMS and PyCOMS, which is the most used version, which is based on Python. So from Python, you invoke different applications, you launch different applications, potentially in different supercomputing centers, and PyCOMS helps you collecting the results from one application and moving those results to the target node where the second application needs to be started on those results. So you do this kind of workflows implemented on several centers. By the way, we have a few courses that are PATSI, Praise Advanced Technology courses on these things, okay? I remember now that October 24, the week of October 24 is the week of OmpSs. No, sorry. That week is MPI plus OpenMP, but it's pretty similar to OmpSs. And in January, Rosa does the course about COMS and PyCOMS. So if you are interested, come to our training website at BSc, and you will see the dates. Okay, now I'm going to concentrate on OmpSs, exploiting tasking. We also provide data directionality hints in the directives that we use to spawn the tasks, so that data dependencies are computed in the runtime system. We support GPUs and FPGAs, and we support multiple address spaces, trying to hide them and let the programmer know about the main address space only, hopefully. So the 2 main components of OmpSs are the Mercurium compiler, which takes the C, C++, and Fortran source and does the transformations, and the Nanos runtime system that I was showing in the first part, which is taking care of scheduling, task management and scheduling for those applications, and also managing the GPUs and the FPGAs. Okay, so the execution model is actually simple and common, I would say. So we have a thread pool model. We don't need to do any parallel directive because everything is in parallel by default. We have one thread that is the one starting the application, this green thing here, and then a number of workers. Some of the workers can actually be representing a GPU or an FPGA. And then tasks are created and inserted in the dependence graph. When the dependencies are satisfied, they go to the task pool. Tasks can be annotated with target CUDA or target FPGA or target SMP or target OpenCL. And this means that the kernel of the task is implemented already in CUDA, OpenCL, or for the FPGA. We do not translate our code onto the device, onto the CUDA or onto OpenCL, but the programmer at this point needs to write the code in CUDA or OpenCL or HLS in the case of the FPGA. So the kernels need to be, let's say, expressed on the language that is there for the device. This is pretty different from one API, for instance. No? In one API, they translate the code for HLS or for the GPU. Okay. Or different also from OpenMP target. No? In OpenMP target, also the OpenMP compiler knows about the OpenMP compiler for the GPU, and they just move the code to the GPU compiler to compile for the target architecture. We don't do that because it's too much work. So yeah, and then the worker nodes, the worker threads get work from the task pool, and if it's SMP, it is executed here. If it's GPU, it is executed on the GPU or on the FPGA. So regarding the memory model, we are trying to get a single memory model, code, data, and stacks. So this is the view that you should have from your application. Trying to avoid to see the global memory or the other memories that we have in the devices, GPUs or FPGAs. And I know that this is not actually fully true, because actually you do some copies there. The dependencies are actually used to do the copies. So actually you are expressing that there are some copies here and there. But our idea is to hide as much as possible, as actually OpenMP does. No? In OpenMP you do target map, and you map some memory between some data from the host memory to the device memory. So it's pretty similar. Okay, so let's talk a little bit about how to program using FPGAs. No? So here I have a very simple example, main function doing a scale task that just scales the data in B in order to get C. And that scale task is actually a task that is expressed for the FPGA, doing these additional directives that help the vendor compiler, in this case the Xilinx compiler, Vivado HLS actually, to do some optimizations on the FPGA. Okay, so the first idea is that we only offload functions. So this would be the function that is actually offloaded. Okay, and it is offloaded automatically by the compiler when we compile this code actually, the full code. Okay, as you can see here, a scale task is actually annotated as a task that gets C and A as input. Actually, it does the reverse. It scales C onto B, which is the output. Okay, so this is actually the way we hide the address space of the FPGA, because we say, hey, at some point, get this data, C and A, onto the device, do the computation, so execute the code, and at the end, put the out result back to the host. And then, in addition to do the tasking, we also do the target device FPGA, knowing now that this task, so this invocation here, is not an invocation into the SMP, but it is an invocation onto the FPGA. And I want to copy the dependencies. This is also the second place where we actually do see the second address space, because copy where? Well, to the global memory of the FPGA. And we can generate a number of instances of this block. Yeah, that would be an IP block actually. Okay, so a scale task, this particular function will become an IP block for the FPGA. As we were discussing in the chat, this is an abbreviation for intellectual property, and my guess is that FPGA vendors at the beginning thought to hide functionality in intellectual property blocks that need not to be open to the general public, so you just use them, okay? In that case, I would say this IP block is actually open because you see here the code. So we target the device, we indicate the data directionality, we invoke the task from the host code. Our compiler, so Mercurium, understands that this is actually a call to a task, not a simple function, but a task, and injects in the middle the necessary call to the runtime system in order to do the copies and to do the execution of the kernel. Both in OmpSs and OpenMP, at least at the very end of the application, a task wait is required in order to just finalize the execution of the task graph. So here the task graph would be actually, as it is, it would be a set of tasks, one after the other, because this is repeated a number of times depending on the iterations of the for loop. So it will be just a chain of tasks. And then particularly with OmpSs FPGA, we have some limitations. For instance, these constants here cannot be defined. This is a limitation in Mercurium. They need to be const int because this way it is a variable, and we don't need to trick with the preprocessor. Constant global variable and task definitions may need to be in a separate file, which is actually this file here, which is actually this file there. No? Because this file needs to be seen by both the Mercurium compiler and the HLS compiler. Well, there should be at least one call to every task, because otherwise we lose the code and the code is no longer used. And although arguments can be structures, this is not fully tested yet. So we use mostly arrays, like in this case. No? C is an array, and we copy size elements from the array. Then the pool of threads take tasks to be executed, and the runtime system, Nanos++ in this case, decides when a thread executes the task, when to execute that task based on user annotations. So when, where, and which data copies are needed. So basically, from the host x86, we have the variables in the memory of the host. We copy the variables on the global memory of the FPGA. Here, actually, in the plot, we read kernel space memory, because this is the way we implement in integrated FPGAs, and global memory, which is the way we implement in discrete FPGAs, the ones connected through PCI Express. Additionally to that, the computation logic may copy the data onto the block RAM that we were seeing. Remember, block RAM is one of the components of the FPGA. And this is done because of speed. Accessing the block RAM is faster than accessing the global memory. Okay, so you copy once, and hopefully you reuse this thing. Okay. And then when the computation is done, the results are put back to the global memory and back to the host if needed. Okay. Good. A little bit the ecosystem, which is this is the picture that I like better because I think it gives an idea of all the infrastructure. You have the source code, no, a scale task in that case, no, the main program, which goes to Mercurium. It is split in two parts. The main program with the call to the FPGA goes to GCC, linked with Nanos, Xtasks, and XDMA, and we can have some instrumentation added there. We get the binary that will run on an operating system that at least has the support for the driver of the FPGA. Actually, the image is for discrete. No, it's for integrated FPGAs, because here we use the QDMA driver in the case of the Alveo boards, which are the integrated, are the discrete ones. And the second part, so I would say this function, which is the one that is targeting the device, no? This function, which includes the two different directives to do the partition of the data, no? We said before, a recommendation is use as many block RAMs as possible. So this is actually what implements this recommendation. Okay, so it partitions the array C completely across the VRAMs. As we have 1,000 elements, we are using 1,000 VRAMs, and we have the data spread on those VRAMs for getting as much data as possible at the same time. So this code goes onto this wrapper and code generation, and everything goes into AIT. AIT is a set of scripts that is particularly well packed to use in a batch mode, Vivado HLS, and the generation of VHDL, Verilog, and then Vivado to generate the netlists, and then linking with our hardware scheduler, some instrumentation, the interconnects, and all this generates at the end a bit stream, which is loaded into the FPGA in order to do the reconfiguration. Okay, so I think that's the complete ecosystem, let's say. Now, an example, which is not a scale task, but matrix multiplication. Okay, so here we have matrix multiplication. It is based on a matrix that has been already implemented as a hypermatrix, meaning that we have an array of pointers, okay, that contains pointers to data. Okay, in this way, the matrix that would be blocked at some point and generating, if we block a matrix, we generate non-contiguous memory references, because memory is usually by rows, and then a block contains different data. So data from different rows that is not consecutive, then this requires a lot of copies and it's not good for performance. So we decided, yeah, we put a matrix of blocks that point to consecutive data. TS by TS is the size of the block, so that with a single data transfer, we transfer everything to the FPGA. So this would be the matrix multiply function that has the usual 3 loops on the matrix multiply that multiplies block by block. Okay, and then we will need the task weight, and we will need the task saying what's an in. In this case, A and B are inputs, C is the output. It is not only an output, it is actually an in-out, because to do a complete matrix multiplication, the formula is the C plus equals. So it's C equals C plus the multiplication of A multiplied by B. Okay, so this is why C is actually an in-out. And then we do target device FPGA with copy depths and the num instances. Okay, so if we put num instances 1, or we don't put anything, then we get an IP block here representing this implementation. So if the implementation of matrix multiply, no? The implementation of this function. Okay, if we put num instances 2, then we get 2 different IP blocks. Okay, and both of them can be used at the same time. No? We can copy data to them, to the block RAMs that they use, enable their execution, and put the results back. Okay, so I think this is the important thing, that we can actually exploit parallelism on top of IP blocks. The other tricky thing is the implementation of the particular kernel. No? The kernel of matrix multiply. Observe that I can write this matrix multiply in CUDA, in OpenCL, or in HLS. And the slide is showing the implementation in HLS. Okay. So this is actually the code that is compiled with the Vivado HLS and the wrapper that we generate. Observe that here we generate a wrapper, okay, and we merge the wrapper with the actual kernel. The wrapper helps us to locate the arguments, no? Put the arguments in the proper way so that the FPGA can actually access them. There is a kind of AXI connection and a port that needs to be taken care of. So in this particular example, the kernel is actually multiplying A multiplied by B and accumulated to C. So we say, and this is vendor tools. This is only AMD childings. Intel Altera has a different set of directives, unfortunately, so they are not comparable. We say, A, this code should go in line in the color. This is one thing that is usually getting some minor performance. So it's good to do the inline. Then we say the factor in which we want to split the variables in the block rams. And we do the partition of the two matrices, the two blocks, A and B, on different dimensions. Why? Because one of the blocks is accessed by by rows, and the other is accessed by columns. No? Usually A would be accessed by rows, so we distribute the second dimension, and the first one, and B is accessed by columns, and we distribute the first dimension. So both of them get distributed on the block. And then we have the inner loops, IA, IB, and ID, okay, which allows us to do the particular implementation of the matrix multiplication, accumulating locally in sum, and then adding to C. This is the plus equals, which makes C to be in out. Okay. There are implementations of matrix multiplication that does just an equal here, so just an assignment of sum to C, IA, IB. In this case, C could be just out because there is no need to read. Okay. And sum is initialized initially to 0, so it will work if we replace this with an assignment and we put out, because initially the values are 0. The second trick that you need to take care in HLS is to do as much unroll as possible in the loops. Because if you don't do unroll, HLS will implement this as a very simple loop doing load, computation, store, load, computation, store, load, computation, store. So it will be sequential, and you don't want that. You want parallelism inside of the FPGA. So with the pipeline, you achieve that this loop actually gets uses the array partition that you have done already to do multiple loads at the same time, do multiple computations, multiply at the same time, and accumulate at the end in C. Okay, so you do this pipelining actually. It's not a full unroll, but probably it's yeah, and you say, I want this loop to be pipelined with an initiation interval of 1, which means that every cycle I want to actually start one computation. Okay. So actually the pipelining does that. No, this is a simple example showing that if you don't do anything, you get a latency of 3 cycles, and I guess the loop latency is actually 6 cycles, and this is actually just done sequentially. If you do pipeline, you can get this overlapping of computation and communication as usually, and you do this. You can achieve this initiation interval of 1, which helps using more resources and also getting better performance. Okay. And then partitioning arrays over the block rams. You have several ways to do that. But the idea is that actually when you do a complete mapping of the data onto the block rams, you use actually all the block rams that are needed in order to put the data as spread as possible. You can also do block, which means that you will be reusing the block rams. This is also useful because it will spend less resources, and with some minimal blocking, you can get all the resources that you need for the particular block size that you are using. Or you can do cyclic. Okay, so this is the 3 distributions that you can have. So think also that it is not always possible to do a complete mapping, because if you have a data that is some megabytes, you will not have enough block RAMs in order to do a complete mapping. Okay, so you will need to use block or cyclic, and this depends on the properties of the algorithm. Okay. So let me show you some evaluation showing that we actually get something out of the FPGAs. Okay. So this is the first evaluation that we did, and this was for the Legato project, probably 3 years ago, where we were targeting actually the Axiom board. Well, no, we were targeting the official development kit that is equivalent to the Axiom board that I have shown. So this means that the matrix multiplication is actually running on 4 Cortex A53 cores with the FPGA. Okay, and then here I'm showing the power consumption that we get out of the execution when we use nearly all the resources, so the FPGA and the cores. Okay, and exactly this is 3 executions. I think it is with 4 cores, 2 cores, and 1 core. And here you distinguish the execution on 1 core and the execution on 1 core. Okay. And the FPGA. So the FPGA power is the yellow line, which, as you can see here, it has some peaks when the execution is done. No? This is done with 4 cores. And here we get higher total power consumption, higher total power core, and also a little bit of consumption here. Okay, in the PS is the cores actually. Very little consumption in the memory, so the DDR power is actually below. Okay, so here you see the consumption that you have in the ARM cores when they execute tasks. Okay, not very power consuming, the cores. They are A53, which are I think they are in order, so not they are efficient in some way. And the peaks of consumption come from the FPGA. Okay, so with more cores you get actually a benefit. Okay, with 2 cores you get less benefit. With a single core you get much less benefit because there are less resources, and the FPGA gets up to what it gets. Okay, actually the performance is shown here. So just 4 ARM cores and no FPGA get roughly 10 gigaflops. With 1 IP core, you get 45. With 2 IP cores, you get close to 80. And with 3 IP cores, this is with NUM instances 3 in the FPGA, you get close to 90, probably, something like this. Okay, and then you can also evaluate the best energy efficiency. No, it's better for energy efficiency to use 2 IP cores, and best for performance to use 3 IP cores. Okay, so this is one of the evaluations. The second evaluation is same algorithm, but now on the Alveo board. Okay, and here you see more matrix sizes. Okay, on the previous example, I think it was 2000 by 2000. So you have here 2000 by 2000, which is the green one, but also others. Okay, with a block size of 256 by 256, a little faster. It's 300 megahertz. And you see that you actually in the Alveo board, you can get up to 250 gigaflops. Okay, which is, I think it's good enough for the matrix multiplication. Okay, I think we have done additional experiments that get a little bit more, but this is probably representative enough without tweaking too much the source code, let's say. And I'm showing also Alveo 200 and Alveo 280. Okay. For instance, we know that we have an issue where when the data is too big, we have probably an issue here regarding the caching that we do in global memory. Probably it's suffering of too many transfers. So the performance is actually heavily reduced. We should actually examine what's happening there. Okay. And yeah, and here actually I'm showing. So this is different matrix sizes. No, this is different matrix sizes, but I'm showing from 1 accelerator to 4 accelerators in the FPGA. Okay, so you see that from 1 to 2 is good, from 2 to 3 is also good, from 3 to 4 maybe we get some dropping in the performance because we are also adding some overhead in the management of the IP cores in the FPGA. Okay, and then I have a small subsection on how to exploit OpenCL kernels that probably will give you an idea on how you can write applications with OpenCL. Okay, so this is the flavor that we call OmpSs at OpenCL. So the compiler is the same, but instead of going to the FPGA phase, it goes to the OpenCL phase, which does a code generation of a particular wrapper, and it joins that with the code for the main application, and we get the binary. In this case, the OpenCL kernels are compiled ahead of time using the OpenCL compiler that we have, but this is not done in execution because OpenCL takes some hours while compiling for the FPGA. Okay, and additionally the results that I'm going to show use a particular implementation that we have in Nanos, which allows to target at the same time the Intel cores and the FPGA at the same time. Okay, so this is what we do when we use an additional clause in the target device. This time is OpenCL. This is the OpenCL configuration, and we say that this particular kernel implements the algorithm matrix multiply, which refers to the C function for the SMP. So in resulting, when we execute, we get an heterogeneous execution, no? As I was commenting before with chillings. We get some tasks going green, let's say, is the FPGA, some tasks going in the blue, which is SMP. So some tasks are executed on the cores. Okay. So with this in an area 10, and these results are a little older, so it's probably 2018, I would say. Observe the full set of experiments that we were able to do. We were able to execute OpenCL in the FPGA in native mode and OmpSs at FPGA. And you can see here we have some drop in performance because of the overhead that we have in OmpSs at FPGA compared to plain execution in OpenCL. Then we can compare OpenCL with the performance in SMP. The machine had 4 core which were dual threaded. Okay, this is why the performance here is reaching 350 gigaflops and then stopping, getting better performance. And this is because they are hyper threads, not very good for HPC, let's say. And actually, you can see also that the FPGA is not much better than a single core. Okay, why is that? Well, here you have optimized libraries. Okay, this is an Intel box, so we have MKL. So we are using matrix multiplication from the MKL library, which is very efficient using the SIMD units of the i7 processor. Then we have OmpSs at FPGA that initially gets less performance, but as soon as we add additional cores and they can use the MKA library, we are getting better performance. And here, even the hyper-threading is helping a little bit. Not much in 8 cores, because here we have another issue, which is we are asking an 8-core platform to execute 9 threads. The 8th cores on the SMP and the support for the FPGA, which also takes cycles. Okay, so not so very good. The machine has also GTX Titan NVIDIA GPU. So this is the performance of OpenCL in the GPU. And this is the performance of OpenCL in a single core. Okay. Maybe not. Maybe it's even on the older cores. I'm not sure about that. But OpenCL by itself is very bad because it's not MKL. It has been compiled by me, not compiled by the vendor. Okay. Then we have the GPU using CUDA, which is actually getting the same performance as the GPU in OpenCL because everything is NVIDIA, so it should be more or less the same. And we can do the same trick, use CUDA and increasing the performance with the cores. SMP1, SMP2, SMP3, and SMP4 are the ones that are getting better, but we have some overhead here. By the way, observe that the two bars is the gigaflops that we obtain after doing some average and the maximum number of gigaflops. Here we have a nice difference between the average, which is low because all cores are already executing tasks, but we have the support for the GPU additionally. And here the hyperthreading is actually not improving the performance. What actually may happen here is that as the GPU is actually relatively good, as you have one core that is one thread, one hyperthread that is not performing well, this is delaying the full execution. So forget about that. And we can even try OmpSs at CUDA and the FPGA, which is that performance here. So here I'm using the GPU and the FPGA to execute tasks. The performance, not very good. Then we move this same implementation to the Stratix 10, bigger FPGA, so we can get better use of the resources and lots of experiments. Okay, so OpenCL at FPGA, the performance on the cores using MKL, also improving the performance of the FPGA. OmpSs at FPGA is not so bad in this case. It's a little down, but not so bad. Also getting better performance. And this, I think this is the most interesting experiment here. We can actually get a combination of FPGA and cores that does some gets better performance, except for the last cores, no? Because this is a 6-core Intel Xeon. I think it's dual chip. This is why we have up to 12 SMPs. But what happens here? That the GPU is much better and just CUDA gets the better performance. Forget about the FPGA, forget about the cores actually. Just use the GPU. Is getting the best thing, 800 gigaflops. Okay. And this is one of the examples where the implements is actually not helping at all. As I was saying before, if you have a device that is very fast compared to others that are slow, either you tune very, very well the sizes of the kernels in each one, or you don't get anything because the GPU prefers to be alone. No data transfers, no slow devices to take care of the tasks, which is what happens in these cases. With 12, it's even worse. The version OmpSs at CUDA and the FPGA, it's not so bad, actually. So it's combining this thing with this thing here, I guess. Okay. Well, it can be used, but you don't get the better performance either. And you cannot even do SMP, GPU, and FPGA and expect something, except that you gain a little bit up to four SMPs, and then not much. Okay, and here we have up to 12, which is actually not performing well. But I think this overall execution, observe that this is not challenge. This is actually Intel box with NVIDIA GPU and Intel FPGA. Okay, and we are able to explore what happens on all the resources. Okay, so I think this is the interesting thing that we can comment about sharing these things. No? There was one question about, for instance, would it be possible to put one big application on the FPGA? Now you have an idea. If the application has a lot of kernels, annotating them will be complex. And targeting CUDA or OpenCL will mean to rewrite them. Okay. Also, targeting one API will mean to write in C++. So if the application is already C++, you have something already there. If not, you need to write in C++ and use the offloading features of one API, which means either Lambda functions or some other, I guess, annotating functions to be offloaded. Okay. How about OpenMP? Well, for GPUs, you can use actually OpenMP. I would say the Intel compiler supports Intel FPGAs, and the GCC compiler, I think, supports both Intel and NVIDIA FPGAs. So to do a first try, it's good, but we cannot be sure that the code for the GPU is optimal compared to our handwritten CUDA kernel. Okay, so you still have some distance to overcome there. Overall complex. I recognize that. So let's see the demo, and we will be finishing with the demo. Unless you have any questions at this point, that we can also take care of. So I guess we are ready for the demo. Do you read properly these windows?
Yeah.
Perfect.
Good, sorry.
So I have here embody, and I have here an interesting thing that I don't know how it will behave and perform, because it is just finished while I was presenting. So this is actually the end of a compilation of the embody application that I have here. Okay. So hopefully it is the end of a successful compilation. So seems good enough, no? And it is actually telling us that we are using this 21% of block RAMs, 9% of DSPs, which is probably not very good, because if you think I have many computations to do and I only use 9% of the DSPs, well, 11% of flip-flops, 19% of LUTs. We have something in Xilinx which is called ultra RAM. Probably our runtime system uses some portion of ultra RAM. This is why we use that. It is equivalent to the block RAM, but I think it's faster. Okay. So the particular application that we have compiled is this one. So observe, we have a main function here, taking a number of arguments. Num-particles is the number of particles that will be simulated in embody, and the time steps that will be computed. Okay, so we will compute 10, 100, or 1,000 time steps with gravitatory relation between the particles. Okay, so it's an embody implementing gravitational, the gravitational computation between the bodies. So we do a few things, and then the important thing is that we do the solve embody wrapper. Okay. This application, in fact, was implemented by a colleague of mine while doing his PhD. So he was using the application to actually show the features that he implemented during the PhD. He was Jaume Bosch. So let me search for, this is the main function here, solve embody wrapper. Okay, it prepares things and calls solve embody task. So this is a task. it is a single task sent to the FPGA, and then you have a task wait. Okay, no flash here. I hope you read these colors also. No flash here means do not bring the data back to the host, because at this point we don't need it. Okay, this is to be able to take the time that it takes to compute in the FPGA without counting for the data coming back. Then we do actually a task wait without the no flash, meaning, hey, now I want the data. And then we take again the time to see how much it takes also the data coming back. So in these benchmarks, we have a lot of features that are targeting our evaluation. Okay, so you may want them or not. This particular, let's say, two-level task wait is actually not needed. With a single task wait, it should be okay. Let's look at the embody task, which is this function here. So this function, it's already targeting the FPGA, okay, and it gets a pair of copies in out, no? The particles here, and the forces, no? So it will compute the forces and compute then the new positions of the particles. So it calls solve anybody and does a task wait in the FPGA. So let's try to see solve anybody. Solve anybody is here. Okay, and as we know that this function is going to be compiled for the FPGA, we say we want this function to be inline, and we call two additional functions in the FPGA: calculate forces and update particles. So we calculate the forces between the different stars, planets, or whatever, and then we have a step of updating the positions of the particles. No, so we compute acceleration, velocity, and position. Calculate forces. Calculate forces is this function here, also inline, and it does in the FPGA the loops traversing the blocks that contain the particles, okay, to compute the forces. So let's go to calculate forces block. Calculate forces block is another task, and it has two instances in this particular compilation. And this is hopefully the compilation that I have done here. We'll see. It has some additional tricks to do the copies between the global memory and the VRAM in a specific way. Okay. It is also inline. It does the array distribution across the block RAMs. So now you can have an idea of if for one kernel I need to annotate all these things, porting big applications will require some effort. Also doing the pipeline and an additional unroll, okay? And we call calculate forces particles. Let me search for that, which is also inside of the FPGA. It's also inline. And this is what probably you were expecting. Finally, the algorithm, okay? So I'm getting positions, I'm calculating distances, squaring the distance, doing the square root of the distance, no? Calculating the force, correcting the force just in case it is 0, and yeah, computing the proper force corrector multiplied by the distance and accumulating to the proper new location. Okay. So there are two main kernels, forces and update. So we can actually see if we have the update particles block, which has also the update of the velocity change and position change. No? So it does the computation of the velocity and the position. Okay. So this application has been compiled twice. And I have one bit stream already loaded in the FPGA. In order to see that we have a bit stream loaded, actually we have a tool which is an OmpSs FPGA tool, which is read bit info. Okay. Read bit info allows us to see what's loaded in the FPGA. Okay. So, well, we have a number of versions, base frequency, more versions, and then what we have here, we have the performance interconnect, we have the extended hardware runtime, and we have the task scheduler, and we have these three accelerators, which are actually the functions that you are seeing expressed as tasks. Okay, particularly calculate forces block and update particles block. We have seen them as these two main things. So this is the type, this is the number of instances, this is the name, and this is the frequency in which we have synthesized. Okay. And we also save here the line that we use to synthesize the AIT, the automatic AIT, automatic I don't get it now. It's not instrumentation. It's well, the tool that we use, that the scripts that we use actually to drive the Vivado. Automatic integration tool, sorry. With the different target boards, that's probably the particular frequency, the hardware runtime, the type of interconnect, blah, blah, blah. Okay. So this is what is there in the FPGA. So this means that I can execute N-body that I have here. N-body just says num particles time steps. Okay. And I know that I have a reference file in this directory for 8,000 particles. The block size is 2048. It is just embedded in the code generation, and 50 time steps. So I can do N-body 892, 50. Okay, and this guy will execute this, and it will come back saying the validation has been successful, hopefully. We have, this is the flush time, this is the execution time, and this is the gigapairs per second that we get. Okay. And now let's try to do the nice experiment of in N-body AIT, I have a new bit stream. In fact, the last bit stream that I had, and this is promising, the last bit stream that I had 39 meg, now it's 41 meg. Hopefully this should be having two accelerators, two instances of the calculate forces. So let's see if I can load. We have this tool also that it's a script developed by us in order to do the loading of the bit stream. So I load the bit stream that I just compiled here, the bit thing. And this is actually now resetting the PCI Express and loading a new bit stream, reconfiguring the FPGA. It will take a few seconds, maybe 1 minute. Anyway, it shows that you cannot reconfigure with high performance. Okay, so I was answering before a question about in OpenCL, actually you can do partial reconfiguration, and I think that's efficient enough. But I mean, even if you spend 1 millisecond reconfiguring, you will get a lot of overhead just by changing the configuration of the FPGA online. Now the bit stream has been loaded. Now I can try to see the bit info that we have here. And it is good because now I have two accelerators of calculated forces block. Okay, so the bitstream actually added a new component, and I should be able to run with the same binary, okay, and using this new bitstream, but I'm going to cross fingers. Well, it went well. Now I'm actually surprised about the performance because it's much, much better than before. Which I was expecting 1 dot something, but we got 3. In fact, the execution time got reduced to 1 second, which is actually pretty good. And it is successful, so the work is done. Okay. So now I'm going just to load the old one. I'm loading the old one just to check that with that old one, I can get at least 1 dot something gigapairs per second, just to be sure. Meanwhile, any questions? I see a question on how do you evaluate the flops for operations like a square key in the Embody app. So for Embody, we learned that the usual measurement that we get is, or that people get, is this giga. It's like gigaparticles per second. So it includes all the computation, square root, computation of the forces, acceleration, no, everything is packed as how many particles do you process per second. And this is what I'm showing here. Okay. So now we have this new bitstream is loaded, and I expect here 1 dot something. That's good. I don't know why that at that time we were getting 0.9, I think it was. Because it is actually possible to use to achieve 1.5 and 3. Yeah, go ahead.
Yeah, just wanted to ask if you can go back to the source code.
Yes.
Where you
Kernel?
submit the. Yes, when you start submitting the very first task. I forgot the name.
So the very first task is this one, but maybe you want to see the place I call that.
Yes, so for example, you say here solve and body task. So
yes,
solve and body
task.
wrapper, yes, it has solve and body task.
And
so this one
is annotated as a target device copy now.
So this is the first time we call something on the FPGA.
In fact, let me. Yes, because this is not annotated. Yes, that's the first thing.
Yeah, so my question is, what is the granularity? Is this block size that you specify? Do I control how many tasks I have?
No, in that case, it's everything. Except
so
that
it's just one single task.
Yes, but there is no copy yet. So it's a task spawned on the FPGA with no data at this point. The data will become when we call the block implementations.
Okay, so for
because
a block
here is where we have the copy in out.
Yes. So this calculate forces block is, you can say, this is the main kernel that is doing
this calculate forces block is the main kernel. Correct.
Okay, and the granularity is the block size that I specify.
Yes, in that case, the granularity is block size, which I think it's 2048 particles. Correct.
Okay. Thank you.
You're welcome. Any more questions?
Seems not. I don't know. We have like 5 other minutes for questions.
let us know. And
Maybe
also
another,
Yep.
maybe another question,
Yep.
if we don't have any more questions. So do you have some kind of a documentation or practical examples we can take to mimic in our algorithms? Some kind of how to, if you want to do this, you can follow this example. If you want to do that, you can follow that example. Or this is more of a